Yes, so for today, we are going to continue our lecture for the theory of structure, SKAA 3243. And we're going to look into the application of slope deflection method to analyze indeterminate frame structures. Okay, so I hope by now everyone has already looked into the asynchronous teaching video that I have prepared for the slope deflection method for beam. There is two conditions for the beam over there. It is without this settlement and also beam with settlement. So please, if you haven't looked into that video and also the link for the derivation of shear force and bending moment diagram, then it is a little bit difficult for you to catch up for today's lecture. So I hope everyone has already looked into it and continue with your own exercise for you to be a little bit familiar for the method. So today we are going to look into the same method. However, we are going to look into their application if you want to analyze frame structures. Okay, so perhaps you were thinking that it is a whole new method if you want to use it to analyze frame. However, all the basic explanation, all the basic procedures and process that you have already learned for the application of the slope deflection method in beam, you are going to apply the same thing for frame. There is no difference between these two conditions, whether it is for beam or frame. The equation is all the same. The procedures are all the same, and also what you have to do step by steps also is all the same. However, when it comes to frame, since you have a different arrangement of the element of the structures, and you have also additional of internal forces, like you are now looking that you have a shear and also tensile forces in your structures, then your job is a little bit more elaborated. You have to be a little bit more careful in your calculation and your steps, but otherwise everything is going to be all the same. We are going to see the full method application for the frame with this one example. Now I have a frame, and for this frame I have three members. So I have member A, B, member B, C, and also members C and D. And this frame is supported with a fixed support at point A and at point D. And it is also supported with a roller support at joint C. And it is loaded with a horizontal load of 30 kilonewton at joint B. And it is also having a point load of 50 kilonewton at midspan of joint of member B and C. So this is a midspan. It's going to be 1.5 and 1.5 meter distance from each joint. And if you can see here, the material properties for the member of the frame are all the same. So I have EI for AB, I have EI for BC, and I have EI also for CD. As mentioned in my previous lecture, you have to be very careful if your members are not from similar material properties, because you have to include it in your equation, otherwise your calculation is all going to be not correct, and it's going to make all the calculation you cannot get the correct answer at the end of your calculation. Now for this example, we are going to use slope deflection method to calculate all support reactions and all the end moments, and in the end we are going to draw the shear force and bending moment for this frame. And as I mentioned also, for this method of slope reflection method, it is similar for the frame and the beam. And the first thing that you have to do is you have to cut your member at both ends to get the slope deflection equation. So if I have this frame, then I will have three members, right? So I have one member, AB, the second member BC, and the third member CD. So I have to, like the beam, I have to cut my member at both ends in order for me to get the slope deflection equation. So for member AB, I will have to cut it at the end of towards the support of A, and I have another cutting towards the support joint B. And for member, the second member BC, I have to cut it at this part, and I have to cut it this part. And for the third member, I have to cut it at near to joint C, and another one I have to cut it near to support D. So right now I have three members with all the cuttings, and at each end I will have my end moment. So from this end moment, I need to use my slope deflection equation in order to get what is the end moment acting on it. Then I can proceed in order to do the equilibrium process to get the internal forces, and from the internal forces I can get the support reaction. So we are going to look into it one by one. Now, after I cut from this, definitely I will have, I will look into it as this is my first member, second member, and the third member. So if I elaborate it, I will have something like this. So this is the first one, my member AB, and from this member AB, I will have my moment. I assume it to be like a in a positive direction. So it's going to be all, my end moment is going to be all in clockwise direction. So this is why this is my member number one, member number two, and number three. Just don't look into the other arrow and notations, otherwise you will feel it is too much for you to get. So we will see one by one. So as what we have done for our beam, after we have cut it, we assume it to have a positive end moment. So this is why for member AB I have a positive moment, okay, clockwise moment, and I make it and I assign it to be MAB. So this is the end moment at joint near to support A for the member AB. So MAB. And at this end, I will have another end moment also. I assume it to be positive, so it is going to be is going to be clockwise. So I give the notation of MBA because it is near to support near to joint B. And for this frame, as I mentioned to you, it's going to be similar to the method that you have learned for the beam. You just need to tilt your head a little bit to left side or a little bit to the right side. Why? You have to look into your member as a beam. A member after that in order for you to proceed easily in this method. So for this, for example, for our first member, I look it into this direction. So I place like my eyes in this direction and I look into it from this one to this one. Okay. So if I want to see it as a beam, I have to rotate it 90 degrees. So it is going to be something like this. I will see it as a beam, and this is going to be MAB. All right, so clockwise, and this is also clockwise direction, MBA. So if I put it into this direction, so there is no difference. I will have to just do all the procedures like I have already learned for my beam element. So as you can see here, from a vertical direction, I have to twist it, I have to rotate it 90 degrees in order for me to look into it as a beam. Okay, so then the other procedures are going to be all the same, whether you have a uniform distributed load. For example, if I have a uniform distributed load here and another horizontal load over here, then the beam is going to be something like this with uniform distributed load and another loading over here. So as you can see here, you can always rotate it, or if you don't want to rotate it, then you can just tilt your head and imagine that you are looking into it from this direction. So for element number 2, since it is already in horizontal direction, there is no problem for me because I can easily look into it as beam element, but I need to define an arrow on how I have to look into it. So I look into it from here to here. So on this angle, since I have already cut it, I have end moment. I notate it as MBC because it is close to B joint. It is still, I assume it to be positive moment, so it's going to be clockwise direction. And similarly at this end, I have another moment at end moment MCB, also clockwise. And about for member number 3, I assume to look into it from this angle, and it's going to be from this arrow to this arrow. Okay, so I look into it from C to D. If I cut it, then I will have an end moment acting on the clockwise direction, MCD, and another end moment acting on it on the close to support D. I notate it as MDC, also clockwise direction. So if I want to look into it as a horizontal member, I just need to rotate it 90 degree, and it is going to be something like this. Okay, so this is the MCD, and another part here is going to be MDC. So now you can see this is element number 1, element number 2, and element number 3. So when I already open it up, then you will look into it and you analyze it as you analyze your beam structure, and it's going to be all the same. However, I repeat it here again, unlike beam, since you're dealing with frame, and frame has more internal forces, you have shear and also you have tensile, so your job is going to be even more when it comes to balancing your forces and also your moment at the for the equilibrium process. Okay, so we will see it one by one after this. Now similarly, after you have identified all the end moments, you also need to identify what is the support reaction that is going to be imposed to your structures based on the support that you have on the joint. So for support A here, since it is supported with a fixed end, so for fixed end it is restricted to move in the vertical direction. It is restricted to move in the horizontal direction, and it is also having a moment on the support. So for this A, for the support A, I will have a vertical forces in my support, so I notate it as AY, and I also have a horizontal reaction for my support, so I notate it as AX, and also I will have a moment, I notate it as MA. This is the assumption of the direction of the reaction that I made in the beginning of my calculation, just in order for me to identify what are the reactions that I need to calculate in my calculation. So other than my end moment, I also need to calculate this one, AY, AX, and MA. So for support A. And for support D, since it is also a fixed end, I will have to identify and calculate what is the DY, what is the DX, and what is the MD. So I have another 3 reactions on my support. For D, 3 reactions for my support at A, and for support C, since it is a roller support, it is only restricted to move in the horizontal direction, on the X direction. So I will have only one support reaction, that is, I noted it as CX. Okay, so this is all the thing that I need to determine in order for me to draw my shear force and bending moment diagram. So we keep the rest first, and in order for me to get what is the support reaction for all the joint here, I need to understand and I need to calculate what are the other internal forces. Okay. So when it comes to frame, as I mentioned to you, you are looking into two types of forces for the internal forces. The first one is the shear and another one is tension. When you deal with beam, you only have to deal with the shear forces because you neglect the tension since there is no changes in the length of your beam. So this is why your calculation is more easy because you only have to look into one internal forces. However, when it comes to your frame, you need to calculate both. You need to calculate your shear and also your tension. So if I take one example of one member, what you did is that for member 1, okay, after you have determined your end moment using your slope deflection equation, after you have determined what is the end moment over here and over there, then you need to use the equilibrium concept or the balancing concept in order for you to get what is the other internal forces. So for member 1, you have the tensile at one end, and another end also you have tensile, and similarly you have shear at one end and another end also you have shear. So I put here for member A, for member 1, the part which is close to support A, I put the tension as TAB. And for the part which is close to joint B, I put the tension as TBA, okay, TBA. And I assume the direction to be in this direction and that direction. And similarly, I will have a shear force at the place that I cut it, and I assume the direction to be in this direction and that direction. So I notate it to be VBA and VAB. As what you have already learned in the when you analyze your beam, after you have determined the end moment over here, okay, after you have calculated the end moment, then you can just do the simple calculation for this element. And from the simple calculation, you can easily determine what is the internal forces of the shear and also the tensile. Then after you have already calculated this part, then you can do the balancing on the other end, because you knew if you have a tensile force of TAB at this end, then it's going to have a similar tension force at the end of the at the other end of this joint, and it's going to be just opposite direction. So if you assume it to be here TAB, so you have another TAB at this point. And if you have VAB, shear for AB at this direction, so the same amount is going to be at the end with the different direction over here. Similarly, if I have TBA over here, only in the opposite direction, I will have TBA, and if I have this direction, then I need to balance it with another direction over here with the same amount. Okay, so from one element, after I calculate the end moments, I can determine these internal forces, and using these internal forces, I bring it to the other end and balance it, and with this one, I balance it at this side. So definitely using this balancing, I can already determine what is the external, what is the forces of the support over here, and using this balancing on the moment over here, I can just balance another one here and another, I can balance over here. So that's basically what you have to do in order for you to get the support reaction. Then once you get the support reactions, you can continue with your shear force and bending moment diagram. Okay, I give you first the procedures of the calculation, since we are going to do it more. This way you knew what we are going to do next. Okay, now after you have solve one element over here, as I have already explained to you from this explanation. Okay, so just now we only look into one element. After you have completed one element and you have balanced it to this part, now this is the time when you have to look into the second element. Okay, after you have already determined what is your end moment at MBC and also end moment at C, and I noted as MCB. So once you get this end moment, then using the simple equilibrium, you are going to be able to determine what is your shear force VBC and also VCB. And after you have determined it, you also can understand how much is the other shear forces. So after you have calculated these forces, again, you're going to do the balancing on the other end and bring it to the other end over here. So until you come to the condition from second element, and you do also to the third element, and from the third element again you balance until finally you are able to get all the internal forces, and from the internal forces again you have to balance in order to get your support reactions. So in the end, these are the forces and moments that you need to determine using the slope deflection equation in order for you to analyze your structures. Okay, so just imagine you have already your support reaction 1, 2, 3, 6 and 7, and you have end moment over here, and from the end moment you have all the shear, you have the tensile. So it is when you look into it at once directly all of it all together, you will feel that you have a lot of things to determine. But the moment you do it like one step to another, and you balance it and you come to another and you balance it again, then this is the time when it is not actually too much. But I need to remind you that most students sometimes they do a mistake in terms of the arrow. For example, if this is this arrow, again they put the other end to be similar arrow like this. So the moment you have a mistake, you did mistake on the arrow, then the whole procedures also is going to be wrong for you. There is no other way for you to be able to do this job in a short duration of time except exercises. So this is why in my lecture I emphasize my students to do more exercise on their own, because only with exercises you are able to train yourself to do it in a very like a short duration of time, because during your test in your exam you don't have too much time in order for you to just like to think what you have to do. It has to be very fast. Okay, so for this lecture we are going to do it very, I think, slow. For those of you who think that it is very slow paced, just think about maybe your other friends that need more explanation. So I will bring it very slow for you in order for you to understand the step by steps. If you feel it is too much slow, then you can just skip it. Okay, now in order for us to look into it perhaps in clear manner, we can do the example, and we can start do the calculation. So as I mentioned to you, for this slope deflection method, you have to do the analysis part by part. Okay, so in here, this is our member, and we decided to cut it at this end and this end, this end, this end, and this end, this end. So I have 3 members right now: 1 member, 2 member, and the third member is over here. So first we are going to analyze the first member. Okay, so this is member AB, from here, member A and B. In order for me to look into it easily, and I can represent it as a beam, I place my view from this angle, and I look it from this direction to this direction using the arrow. Okay, so from here I rotate it 90 degrees. It is going to be equivalent to this member. So right now I have member A and B with the length of 3 meters, and I assume my end moment to be clockwise direction for MAB, and another moment clockwise direction MBA. And this is my fixed end moment since I have no external forces acting on this member. So my fixed end moment for AB is going to be 0, and fixed end moment for BA is going to be 0. And using the slope deflection equation, I can determine my end moment using this equation. Okay, so it is a standard equation, as I have already explained to you in my previous lecture, how we came out with all these parameters over here, and we just repeat it. So for MAB, it's going to be 2 EI over L. So since it is A over here, you will have 2 theta A plus theta B minus 3 delta over L plus FEMAB. So for this frame, since this is a fixed end, okay, so fixed end at joint A, we will not have any deflection at joint A. So for this one, your theta A is going to be 0 since it is fixed support. So I cancel out to be 0 since it is fixed support. And since I have also joint C is supported by the roller, there is not going to have any horizontal movement for joint B as well. So in other words, my delta is going to be 0. Okay. So delta is going to be 0, so I cancel out here. Delta is going to be 0. FEM, since there is no external forces, then I can also cancel out to be 0. I solve this equation. L is going to be equal to 3, the length of AB, and I will have the first equation for my calculation. Now I need to determine what is the value of MBA. So for MBA, it's going to be 2 EI over L times 2 theta B, okay, plus theta A minus this 3 delta over L, and plus FEMBA. Since there is no theta A, because it's going to be a fixed end, so I cancel out 0. There is no horizontal movement, so delta is going to be 0, and there is no external loading, so FEM is going to be 0. Now I solve this equation. I will have the second equation over here, right? So this is for member AB. So member AB is done. I go to member BC. So for member BC, it is this one, right? So it is already in the horizontal direction. There is no issue of rotating it because it is already in horizontal position. So I have member BC. Member BC is 3 meters, and at mid-span, I have 50 kilonewton as external loading, and I assume my end moment to be clockwise direction, so I put it to be MBC, and another end moment in the MCB, and first I need to calculate how much is my fixed end moment, right? So for fixed end moment, since I have external force acting on the midspan of BC in this direction, so my beam, my structure is going to be deflected in this direction, right? So due to this vertical load, it's going to have this deflection. In other words, my theta is going to be here, clockwise direction, and another one here is counterclockwise direction. Fixed end moment, the job of fixed end moment is to push my member back to the original position. So in order to push this member back to original position, I will have my fixed end moment at the opposite direction. So I noted it as FEMBC. Okay, so it's going to be counterclockwise, and since this one is in this direction, so in order to push it back to the original position, I will have my fixed end moment acting in a clockwise direction. So I notate it as FEMCB, right? Okay, so since this one FEMBC is counterclockwise, so I have negative. Since this FEMCB is clockwise direction, I have positive. This is the equation I can use in order to determine what is my fixed end moment if I have the loading condition as this one. So P is this P, and this is A, and this is B, and this is total length is L. So I just need to put all in this equation, and I have my FEMBC to be negative 18.75 kilonewton meter, and FEMCB positive 18.75 kilonewton meter. I use this value into this equation. Okay, so this equation over here, and this one is over here. Now, once I have these values, since this is both is not a fixed end, so I have my theta B and also theta C. However, since it is supported with roller support over here, there is no vertical movement because of also the fixed. There is no horizontal movement because of the support over here. So my delta is going to be 0. So I cancel out delta. I put in all the values. Then I have my third equation in the form of theta B and theta C. Okay. Similarly, for my moment at CB, I have my equation 2EI over L to theta C plus theta B minus 3 delta over L plus FEMCB. I have already calculated my FEMCB. I don't have any delta, so 0. And I have this equation number 4 in the form of theta B and theta C. Okay, so this is for member BC, and I have the last member of member CD. Member CD, if you can see here, it is this one, okay, the third member, and this is in the vertical direction. So I place my view in this position, and I look it from this end to this end. So if I want to represent it as a beam element, I just need to rotate it 90 degrees this way. Then I can look into it as C and D. Right, so from this angle, I rotate it 90 degrees upward. It's going to be looking like this, C and D. And I will have my end moment over here, clockwise direction, and another end moment over here, clockwise direction. So when I already assume this way, my calculation is going to be very straightforward. So this is the one that I mentioned. So from this position, I rotate it to this position, and since there is no external loading, then my FEMCD is 0, FEMDC also is going to be 0. And since this roller prevented from moving horizontally, so my delta also is going to be 0. And since the support at D is also fixed support, then my theta D is going to be 0. Now, using this slope deflection equation, I just cancel out what is the thing that I don't have, and in the end, I will have my fifth equation in the form of theta C. Now for end moment of DC, again the same procedures with the equation of MDC. I will have my sixth equation in the form of theta C. Now I need to solve this equation because all of them they need to be, they're all in the form of theta B, okay, in the form of theta B theta C, and also in the form of theta C. So I need to calculate first what is this theta B and theta C in order for me to get what is the final value of my end moment at each end of my member. So for this one, I need to solve EI theta C and EI theta B using the equilibrium at my joint. Now, if I look into the equilibrium of joint, Okay, so I go back over here. Now, if I have already calculated what is the end moment over here, I have my equation. And to balance this end moment over here, this is the clockwise direction. I need to balance it at the other end of my joint over here. And this one also, to balance this end moment over here, I need to have another moment at the other end of my joint here with the opposite direction. Okay, so using this one joint, I need to find my equilibrium in order for me to find what is this MBC, what is MBA. Then using this equilibrium, I can determine the others. Okay, so this is one. We come to the equilibrium over here. So for equilibrium at joint B, this is what we have, MBC in the counterclockwise direction and MBA also in the counterclockwise direction. So hold on a second, let me see. Okay, so this one is wrong. Okay, so since this is the clockwise direction, so this one should be counterclockwise direction, okay, because it's going to be opposite of the other side. This one is clockwise, this one is counterclockwise, so this is correct. So I take this joint B here in order for me to take the equilibrium condition. So at joint B, the equilibrium of moment has to be 0, okay, so I will have MBA plus MBC has to be total to 0. Now I just use this MBA and MBC equation. So I have this one, MBA, MBA, so not this one. So I use this one, MBA, so equation number 2, and MCB, equation number 3, equal to 0. So this is going to be very straightforward for you to solve it. It's going to be equation over here. And for equilibrium at joint C, all right, so for equilibrium at joint C, right now I assume it to be clockwise direction, MCB, and at the end of this joint here, I will have a counterclockwise direction of MCB, and since this is clockwise direction MCD, I will have it to be counterclockwise direction of MCD. Now I have the second equilibrium for my joint in order for me to solve this equation over here. So I will have MCB plus MCD equal to 0, okay, for joint C. So I have this one, then I just need to use the equation that I have already prepared, MCB and MCD. So I have MCB, then MCD, then I just need to put it into my equation and I will solve it. So using this equation, and I'm sure you have already learned how to solve this type of equation, you will have the value of theta B and theta C, and using this theta C and theta B value, put it into your equation, you will have your end moment for AB, end moment for BA, MBC, MCB, MCD, and MDC. Now, the moment you calculate it, you will see this is 6.25 positive, positive, negative, negative, negative for the others. So this is the moment. This is the time when you have to correct the direction that you have first assumed it to be positive. Okay, so for the value which is already positive, then you don't have to change it because it's going to be positive. But this value negative, negative, and negative in here, you have to correct it in your drawing in order to show that it is actually a counterclockwise rather than clockwise direction as you have predicted it before. So now I just take this value, okay, positive 6.25, positive 12.5, and I just draw it into my diagram. So this is member AB, the first one, member BC, and member CD that I have already determined. So this is clockwise, positive 6.25, and another positive 12.5, also clockwise direction. However, for the member BC, it's going to be negative 12.5 and positive 12.5. So I will have counterclockwise direction, negative, and clockwise direction, positive 12.5. Now on the other, on the third element, I have negative 12.5 and negative 6.25. So it's going to be counterclockwise direction, 12.5, counterclockwise direction, 6.25. So these are the end moment that I have already determined. Now the next part that I have to do is to find the internal forces, right? So the first thing that I can do, the moment I have the end moment over here, I need to balance it on the other part of the member. So if I have in here clockwise direction 6.25, so I need to balance it with the counterclockwise direction 6.25. And since this one is clockwise direction, so I need to balance it with counterclockwise direction 12.5. Now I have here counterclockwise, so this one is going to be clockwise direction 12.5. And this one, since I have a since I have clockwise direction, so I need to balance it with counterclockwise 12.5, and so on until I come to the end over here. So the moment I come for example, this one is going to be a counterclockwise, so this one should be clockwise direction 12.5, and this one is counterclockwise, so I have here to be clockwise direction 6.25. Now since there is no other moment acting over here, so since this is 6.25, then I can always know that there's going to be the other direction of my moment, so I can easily determine what is moment A and moment D. Okay, so we can go to, okay, so this is our this is all the balancing of moment that we have already done at the other end. And once I have already balanced the moment at the other end, I can first get what is the shear force at the members. Okay, the shear force, and also the tensile for the shear force for this one first, because I couldn't get the tensile before I do the other part. Now in order for me to get the shear force at member AB, it's going to be same procedures like what you have already learned in your beam. I assume the shear force for towards the end of A is going to be VAB, and towards the end of B is going to be VBA. I assume the direction to be in this direction first. Now, in order for me to get it, I just take the total moment at point B to be 0. So I have, since this shear force over here, this force is going to rotate in order to get to B, it's going to follow the clockwise direction. Okay, so it needs to follow this side. So it's going to be positive. So this is positive VAB, and the moment arm is 3. So 3 over here. So moment arm times the force is going, and since it is a clockwise direction, so it's going to be positive. So 3 times VAB, and this one is clockwise direction. So I have positive 6.25 for the moment, and this moment over here also is clockwise direction. So I have positive 12.5 equal to 0. Okay, so if I solve this equation, I will have VAB equal to negative 6.25. So what meaning is that the direction that I assume to be in this direction before is wrong. So I have to correct the direction to be from here to here, 6.25. So this is the correct direction and the value of my shear force at member AB. Now, in order to balance it, I can just use the simple equilibrium, total Fx equal to 0. So I assume to be this direction as positive, and this one, sorry, to be the direction of this one to be negative. So I have negative 6.25 plus VAB. Okay, VAB, I assume it to be this way, is equal to 0. So from here, I will have VAB of VBA to be 6.25. So it is in the opposite direction. So one is 6.25 this direction, and another one is 6.25 this direction. So I have this value and the direction of my shear force at towards the B end. Now, if I have this value over here, I can balance it towards the other end of my support. So if this one pointing this side 6.25, I need to balance it to be having something like this. So this one 6.25. And if this having a value of 6.25 towards this direction, I need to balance it towards this one 6.25. Now I have for this end 6.25 this direction, and this direction also 30 kilonewton. So I can balance towards this direction to be 36.25. Okay, to balance this point over here. And since I have 36.25 pointing this side, so I have to balance it towards this one also 36.25, but in the different direction. Okay, and since this one is 36.25 at this direction, so I need to balance it. Hold on a second, this one is okay. So since I have to have this direction from here to here 36.25, I need to balance it from this one to this one 36. Okay, now it's better. 36.25. Okay, to balance this side. This one 36.25. All right, so since this one 36.25 from this direction to this direction, I need to balance this side also 36.25. So as you can see here, I balance it until I couldn't do balancing anymore because I don't know there are two unknowns over here. This is I don't know this one and I don't know this one, so I stop this side. Okay, so I balance it. Whatever I have value in my hand, I balance it until I couldn't do more, and I have to do on the other elements. So I have already do the member AB. Now I have to do the other members in order to get more internal forces for my joint. Okay, so this is the thing that we have already calculated, and since for this one we can continue balancing until we balance this one. Also we have already looked into it just now. After from here we balance it until this side. Okay, balancing at point D, point B. And after that, we need to solve the internal forces for member BC. Okay, so this is our second element, member BC. Now for member BC, again, it is very straightforward for you. We can get the shear force at member BC using the simple equilibrium equation. And I assume my shear force at the BC is going to be following this arrow, and my CB also is going to be following this arrow. So in order to determine that, I need to get what is the total moment at C equal to 0. And since this shear force that I assume to be in this direction is going to follow this clockwise direction, so it's going to be positive. Okay, so this is what positive VBC times the moment arm 3. So I have VBC times 3, and so for this one, I have also the external force 50, since in order to get to C, it follows this direction. Okay, so it's going to be counterclockwise, so it's going to be negative. So I have negative over here, and this one is 50. Moment arm is 1.5. So I have 50 times 1.5, and I need to add the moment that is also acting at both ends of my member. So the first moment is going to be this one, and it is counter clockwise direction. Okay, so it's going to be negative 12.5. So I will have here negative 12.5, and this one is positive because it is clockwise direction 12.5. So I have plus 12.5 and equal to 0. I solve this equation, and I will have VBC equal to 25. And since it is positive, so meaning the direction that I assume to be before pointing this one, this side is going to be correct, 25. And for the total Fy equal to 0, I have 25 minus 50, then I will have also 25 pointing upwards. So VCB is going to be also positive, 25. Then now I have the forces for my BC, the internal forces, to be 25 and 25 over here. Now, if I have 25 at this one, I can balance it towards the B joint. So if I have pointing upward 25, I have to balance this pointing downward 25. Okay, so since there is no other external or internal forces over here, so I can balance this one with another force at the end over here. Okay, so in order to balance this one, I can have balance 25 here, and since this one is balanced with the upward, so this one I can balance with downward 25, and in order to balance this one, I have another force over here, 25, pointing the other side, and in order to balance this one, I need to have another one pointing downward 25, and in order to balance this one, I will have something over here 25. Okay, so now I have already balanced this side. How about the other side? So if I have 25 over here pointing upward, now I need to balance it with pointing downward 25. There is no other forces to be balanced. So in order to balance this one, I have 25 pointing upward. And in order to balance pointing upward, I need to balance with pointing downward 25. And in order to balance this one, I balance with 25 over here. To balance this, I have pointing upward 25, and to balance this one, I have pointing downward 25. So this is my y, a d, right? I think we have a dy, sorry. So this is my my force of my support for my support reaction. Okay, so dy will be equal to 25 pointing downward, and this is the ay will be 25 over here, right? So this is the time when I already stopped balancing the other part. Now I have to look into my third element. Okay, so this is the thing that we have to we have balanced all together, and from there we balance it with the other one. So we need to get what is the shear force at member CD. Okay, so member CD over here, number 3. Now for member CD also, we look into this direction. So we'll have VCD and also VDC over here. So similarly, I will have to take moment at D equal to 0. So this one, since it follows this direction, is going to be clockwise direction. So VCD positive times moment arm 3. And I have this one to be counterclockwise, so it's going to be negative 12.5, and this one also counterclockwise, 6.25, so negative 6.25 equal to 0. Now I will have my VCD to be equal to positive 6.25 and VDC to be equal to negative 6.25. So meaning the direction that I assume is going to be like this one and also like this one. So this is not in the correct direction that I have predicted to be in this direction, but it has to be corrected this way. So once I got my VCD to be in this direction, 6.25, now I have to balance it with this angle. Okay, so this one also is going to be 6.25, and if you look into this joint, I have all the forces that I need in order for me to calculate how much is my the force in my joint for CX, right? Because I have already all the forces that I have, so definitely I can easily calculate what my CX is. And I have to balance also this one at the other end of my calculation. So if I have 6.25 this direction, I need to balance it with another 6.25 at this direction, and in order to balance this one, I have to have another 6.25 at my support. So this is my dx at this direction. Okay, now in order to get my reaction at support C, I just need to do total Fx equal to 0. So in the x direction, I have this direction of forces, 36.25, and another one in here, opposite direction, 6.25. So if I balance this one, I will have my Cx equal to 30. Okay, so this one, this direction, 36.25, minus this direction, 6.25. So I will have this direction to be 13 kilonewton. Z direction. Now for CX also I have already completed it, and this is all the internal and external forces that I have already calculated for my joint. All the joint and also all the support reaction also has been calculated over here. So from this information I can draw my shear force and bending moment diagram. Okay, so after you have calculated all the internal forces and support reaction, you can proceed with drawing of the shear force and bending moment diagram. Before we continue with shear force and bending moment diagram, do you have any question that you want to ask? Do you have any question, class? Okay, so there is no question. I will give you 10 minutes break. You can go back to the calculation before to just or have some refreshment, and after 10 minutes we will come back and we will continue with the drawing of shear force and bending moment diagram. Okay, so we break until 12:20. We see each other at 12:20, then we continue again. Okay, so we take a break for a while. Okay, so these are all the internal forces and support reactions that we have already determined using our slope deflection method. And from this diagram, you can see that for support A, we have horizontal support reaction AX of 6.25 from this direction to this one, and we have AY 25 kilonewton pointing upward. We also have moment acting on support A in the direction of clockwise direction, 6.25 kilonewton meter, and for support D, we have a counterclockwise moment of 6.25 kilonewton meter. We have also horizontal horizontal force acting on this direction, 6.25 kilonewton, and we have vertical support reactions, dy of 25 kilonewton. And for support C, we have horizontal support reaction, Cx of 30 kilonewton, acting from here to this direction. So this are all the thing that we have already determined on the support reaction. And in order for you to draw your shear force and bending moment diagram, you have to do it part by part. Okay, so for a frame, you have to draw your shear force and bending moment diagram element by element. So the first element that you're going to draw its shear force diagram is element number 1, element AB, and after that we're going to look into our member BC, and then we are going to draw it for our member CD. Okay, so first we look into this element in which we have all these internal forces acting on it. Okay, so if I take this member over here, and this one, okay, then I take it to this next slide. It is all exactly like this. So you have your end moment, you have your shear force, and also you have your tensile forces acting on member AB. And in order for me to make it easy for me to draw the shear force and bending moment diagram for me, I rotate it 90 degrees towards this direction in order to look into it as a horizontal member. So from here, if I rotate it, it's going to look like this one. Okay, so from this one, I rotate it to this direction. It is going to be like a beam member from this point A to B. And in order for me to draw the shear force diagram, I just need to take all the forces over here. So if I rotate it, I will have my shear force acting downward. Okay, 6.25, and another one here acting upward, 6.25. And I also have the axial force, okay, over here, 25 kilonewton and 25 kilonewton. However, since the frame doesn't have any changes in its length properties after the loading, so I can I can cancel out these axial forces. In other words, I can neglect it, the value. So I have here right now 6.25 downward and 6.25 upward. And based on our previous lecture on the drawing of shear force and bending moment diagram, we have the general guidance in order for us to determine the positive and negative. So if you have arrow of pointing upward and downward over here is going to be a positive shear. However, if you see here, our shear force is pointing downward instead of upward, and instead of downward over here, it's pointing upward. So it's going to be negative and negative, because pointing up and down over here is going to be positive, but for us, is pointing downward and upward. So this is why, if this is our reference line, and it's going to be negative. So we put here negative 6.25 because it is opposite direction of our guidance, and since it is also opposite to our guidance, it's going to be negative. There is no forces in between of point A and point B, so I can just make it a straight line between point A and point B. So I have a negative 6.25, negative 6.25. I joined them together, and this is going to be a negative shear force area. So after I draw it, I can again rotate it back to its original position in the vertical direction. So I will have something like this. Okay, so A, B, and it is going to be towards this side, negative 6.25, negative 6.25, and the area is going to be negative shear force area. So this is going to be member AB. For member BC, there is no complication to it because it is already on the horizontal position, and I have 25 kilonewton, 25 kilonewton, and I have only 1 point load 50 kilonewton. So this one, I get it from here. Okay. All right, so this is the one. And since there is no changes in my length of my frame, so I can just cancel out this 36.25 kilonewton, and I remain with this 25 and 25 and external loading of 50 kilonewton. So this is where I got to this point, and our general guidance says that positive is pointing upward positive, pointing downward to be negative. And if you can see here, our direction of shear force is pointing upward, so it's going to be positive. Now I put it on the upper part of my line. This is my reference line. Okay, so for shear force, positive is towards the upper line. So positive 25, and this angle here, since it is in the opposite direction, so it has to be negative. Negative is in the bottom part of the line, so negative 25. How I can connect these two point for the slope of my shear is going to be based on the loading. So since there is no load on this point between 25 and 50, so I just have a straight line and I have external loading of 50, so it's going to be minus 50, so I go to this one, and since there is no this one is going to be negative 25. Since there is no load between these 2 points, so I just have to make a straight line for these 2 points. So I have a shear force diagram with positive area and also negative area on the other on the second half of my member BC. Now I keep this one. And I go to my member CD. So my member CD, similarly, I just take this. Okay, so I use this one. So my member CD, if you can see here, I have 6.25 and another 6.25 at this direction. And this one can be canceled out because there is no changes on my the length of my member. And I will have these internal forces of my shear force, 6.25, 6.25. And in order for me to make it easy for me to draw it, I just rotate it upward 90 degree and it becomes this direction. So I have pointing upward 6.25, pointing downward 6.25, and if I compare it with my reference guidance, pointing upward has to be positive, downward has to be negative. Upward positive and downward here positive. So if I compare it with my drawing here, both are pointing upwards, so both are positive, and both are pointing downwards, so both are positive. So it's here. So positive 6.25, positive 6.25. This is my reference point. Positive is always upward of the diagram for shear force. Then I will have my shear force diagram to be positive over here. Now, in order for me to go back to the original position, I just rotate it back 90-degree downward, and it's becoming this way. So this is the shear force of my member CD. Now I just combine this one that I have already drawn for member AB. So remember, this is the reference line for my member AB, and it is pointing towards this side, to the inner part. And for the BC, there is no problem for it. And this is the reference line for my member CD, and it is pointing towards this direction. So I just take all the shear force diagram that I have already drawn, and I put it in my in my whole frame. So this is for member A, B, C, and D. So I mark it. This is my reference point and my reference line. And be very careful that the negative area is the inside part, positive area going to this side, and this is upper side, and this is downside. So this is my shear force diagram for my frame that I have already analyzed it before. Now I moved back to drawing the bending moment diagram. So for member AB, similarly, I just take what I have already done over here, member AB. And for member AB, I have my end moment, okay, end moment 6.25 clockwise direction, and another one clockwise direction 12.5 for my moment for member AB. So I take this information. Okay, so I have 6.25 clockwise, 12.5 clockwise, and I look into my my beam in my member like this one. So if I rotate it, then I can look into it as this direction. Okay, so this is AB, and this is 6.25 clockwise, 12.5. And for the guidance of our moment of our bending moment diagram, if it is pointing upward like a smiley face over here, arrow up is going to be positive. So if I have my line, my reference line over here, okay, so since this is both in the arrow is pointing upwards, so it's going to be positive. And be very careful for bending moment diagram. The positive moment is going to be on the bottom side of the diagram, so this is going to be positive 6.25, and this one has to be pointing upward, but this one pointing downward, so this one is negative. So negative 12.5 towards the upper part of the diagram, so negative 12.5, positive 6.25. And how I'm going to connect these two points, I need to refer back to my shear force diagram, and I knew that the slope for my bending moment is going to be depending on my slope of my on my shear force diagram. So is it going to be negative V? Okay, so since it is negative 6.25, so it's going to be negative 6.25, so it's going to be positive 6.25. So since the slope is positive, so positive is pointing upward like this. So I can just like connect them upward like this one. Okay, and after I have connected like this, then I have to put it back to the original position. I rotate it back upwards. So when I rotate it back upward, it becomes this way. So this one is positive moment, and this is negative moment, and this is the area of the shear force of the bending moment diagram, negative, and this is the area of positive bending moment diagram. So I have already drawn the shear force diagram for member AB. Now for member BC, I have the end moment 12.5 counterclockwise, and clockwise end moment 12.5. This one also is coming from the equation over here. Okay, so we have counterclockwise 12.5 and also clockwise 12.5. So for member BC. Now I just take this one towards this. Okay, so this is my end moment, and I have also one external loading, and my guidance for the bending moment diagram is smiley face positive. So this is going to be the opposite direction. This is upward, but this is downward. So it's going to be negative 12.5. Negative has to be on the upper side of the diagram. So negative 12.5. And how about this one? Also opposite direction. So another negative 12.5. So I put it here, negative 12.5, negative 12.5. How about the middle part? How I can just connect these two together? Now, I need to look into the shear force diagram for this member. So my shear force diagram is something like this. I have positive, okay, it's positive shear, 25 here, and also negative shear on the other side of my member. And I knew between point B and E, the slope is going to be dm over dx negative v. And since I have my shear force here is the positive 25, so I will have the slope negative times positive 25. So I will have negative 25. So the slope is going to be pointing downward between point B and E. B and E is going to be pointing downward, and between point E and C, the slope dm over dx is going to be negative times negative 25, so times negative v. So since I have here the shear force diagram, and the shear force is going to be negative 25, so when I times this one, it's going to be positive 25. Positive slope is going to be pointing upward for my bending moment diagram. So I take this. Okay, so it has to be something pointing downward and pointing upward. But the middle part in here, I knew it is going to be until point E. However, I need to determine how much is the maximum moment at point E. So in order for me to get the maximum moment at point E, is going to be a moment at B, okay, plus the area of the shear force diagram area of this one. So I have negative 25, so moment B, negative 25, and the area of this moment is going to be 25 times 1.5, because this is just the area of a rectangle area, positive 25, height, and the length is going to be 1.5. So if I solve this one, I have positive 25 kilonewton meter. This is the maximum moment at point E for my member BC. Now, for my member CD, I have this end moment over here, counter clockwise and also counterclockwise. So both are negative 12.5 and negative also 6.25. And if I rotate it upward, in order for me to look it easy, so I have something like this. Okay, counterclockwise, and also this one counterclockwise. And my guidance for moment diagram is positive upper smiley face. So this one is a different direction, opposite direction, so it's going to be negative. So negative is on the upper part of my diagram, negative 12.5, and this one is same direction, so it's going to be positive. Positive is on the bottom part of my diagram, so it's going to be 6.25. So I have negative 12.5, positive 6.25. There is no changes in the middle of both point, and in order for me to know how I'm going to connect them, so the slope is going to be dm over dx equal to negative v. V is a positive 6.25 for my shear force diagram, so it's going to be negative 6.25. Negative 6.25 is pointing downward. Okay, so this is going to be my bending moment diagram I have, and this is my reference point for my member CD. And if I rotate it back downward like this, I will have my C, okay, negative 12.5, and D, positive 6.25 over like this. So be very careful with the area of this one. Don't mix them, because you're going to combine all the bending moment diagram. Okay, So for this one, you have the first one that you have already drawn, moment member AB, like this, tick tick. Now like this, and this is member BC, and this is member CD that we have already drawn. So you have negative, positive, and everything. And you also can obtain the deflected shape of the member, because sometimes in the question it also requires you to draw the deflected shape of the member. Now, in order for you to draw the deflected shape of the member, if the moment is positive, the deflected shape is going to be upward like this, conquered up, and if the moment is negative, it's going to be conquered down. So if it is positive, it's like a smiley. If it is a negative moment, it's going to be deflected shape, a bit sad face. And since this is negative, another sad face, and it is positive, smiley face, negative, sad face, and this one also negative moment, sad face, positive moment, smiley face. So if the question requires you to draw the deflected shape of the structure, so it's going to be something like this. So it's going to be the smiley face, and then sad face, and another sad face, and this one is going up, and another going down, and this one is going up, and this one is going down. So this is basically how the deflected shape of the frame based on the external force that it has, and also the support reaction that it has for the condition. Okay, so basically that is the end of our slope deflection method for frame. If you have any question, you can ask right now.
Sorry, doctor, I have a question regarding the balance in the moment at the other end. In the
Balance of moment, okay.
Yes.
It will be something like here.
Yes, in point C, shouldn't be the 12.5 in the opposite direction of the other one?
How is it?
In the point C.
Point C, okay.
Yes, the left one, 12.5.
You mean this one?
Shouldn't be in the opposite direction of the other 12.5?
Because this one is clockwise, right?
And this one should be anti-clockwise.
Oh yeah, so that will be a little bit the mistake over here. So you can just correct them.
Yeah, and also in the point B, also the same thing.
Okay, so you can just correct it. I may having so this one is clockwise.
This one is correct, but the other
this one.
end.
The other end point over this one, is it?
The B point 12.5 in the downside.
There is this one.
I can't see there.
Okay, so 12.5 is counter. This one is clockwise, and this one is counterclockwise. Is correct. This one is clockwise direction. This one is it? You mean?
This one, yes, yes,
Yeah,
this one.
so this one is counterclockwise. I'm
Okay.
sorry. So in order to balance all the moment, it has to be all in the opposite direction. First, you determine the member. Then from that member, you go to the other direction with all in the opposite direction. Okay. I think I have also made a mistake over here. So if this one is pointing upward, this one should be pointing the other direction, right? 25 over here, because
Yes, but it's corrected in the other slide.
Okay, and this one has to be like this. All right. Okay.
Oh, doctor. If there is settlement, how should we draw the deflected shape?
The settlement. Okay, for the settlement, first you need to get the all the moment, and from this moment then only you can draw the deflected shape. The concept is all similar. The only difference is until you get the moment of that part, but the concept is all similar. Like this one, it's all similar. Okay, it's all similar until you get the final moment.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.